So today we're going to be talking about a topic that is not on the midterm, and attendance is not required, and I need to turn the screen on. So we're going to be talking a little more about classification. We'll see a little bit of review, and we're going to talk about regularization. So, as a bit of a review, today some of it is pertinent to what you'll be doing on the midterm, even though none of the new material today will be on it. Being here, I think, should help to some degree. So some key ideas from what we were doing before. We had this idea that a problem we want to solve is classification. We in this class so far, and indeed almost entirely, will only focus on binary classification. Does a thing belong or not to a class? So a classifier gives you a prediction of 0 or 1 for our y's, and that's in contrast to linear regression, which was any arbitrary number. Logistic regression is a technique which effectively, the job of logistic regression is to find a function that will estimate the probability that an observation belongs to a class. And we need a decision rule, as we talked about in the last couple lectures, to convert from a probability to a class. And typically what we do is we just threshold. So for a threshold of 0.5, we would say we will classify x as a 1 if the probability is bigger than a half, and 0 if it is less than a half. All right, nothing new there. All right, but that's the groundwork we need. Okay, so let's talk about decision boundaries, which is a really nice way of thinking about classifiers. So as you know, our regression models, they give us probabilities, and what I'm showing on the bottom here is a curve, which the blue to orange curve shows the probability that our model thinks that a team will win. This is using the same data set from the last couple of lectures, based on the field goal percent difference. You can think of this as the difference in the shots that the two teams made. So if you're shooting better, you'll be over here. If you're shooting worse, you're over there. The gray dots that you see are the actual data that we use to train this model, and the blue to orange curve shows the probability that our model predicts. And I've chosen this curve because it'll allow us to better visualize what I mean by a decision boundary. Now here, I don't care about the data, so I'm going to take it away. And I'm just going to focus on the predictions, our probabilities. And I will note that if we pick a threshold, then, as we've been saying, we get a class back. So if I pick the threshold t equals 0.3, that's the probability threshold, then everything over here on the left will be lose, and everything up here will be win. So if we think about how our function changes, this probability here, once we apply a threshold, it looks like that. It's either 0 or 1. Okay, so let me do that again. Right? So by picking that threshold, we take our curve and basically snap it, and the orange part gets stuck to the top, and the blue part gets stuck to the bottom. Okay? So the effect here is that any x, in this case x is the field goal percent difference, that is less than some xt, these will all be lose, and everything bigger than xt will be win. Where did this number come from? Where did negative 0.0277 come from? I have like 82 of you. What do you think? I mean, it's kind of obvious, maybe. So where did that number come from? Yeah. Exactly, yes. That is the x that when you plug it into your logistic regression model, you get a probability of exactly 0.3. Okay. So ultimately, that will be a function of our model parameters, our betas, and our t. Okay. So that is in one dimension what happens when we threshold. We take a nice smooth curve and we make it into just a 0, 1, right? You have zeros and ones. Okay. Now this right here, what we can note is that this point, it separates loss from win. Okay. Let's say we look at 2 dimensions now. Let's look at a model which tries to predict the probability that you win based on 2 things. How much better was your team shooting than the other? And how many fouls did your team have? So a personal foul in basketball is you do something a little bit against the rules, and it can affect, according to my classifier, how likely it is that you win. So this picture here shows the 2-dimensional analog of this blue to orange curve here. So now we have 2 features and 2 parameters. Actually, we have 3. I'll get to that in a second. But we have two features. We have our percent shots made difference and our number of fouls difference. And this is, I'm just showing it to you from two different angles. So these are literally the exact same thing from two different angles. So you can see it kind of looks like if you took a sheet of paper and like bent it and had two planes at the top and bottom here. And it looks like that the better you shoot, the more that you're likely to win. And let's see, the fewer fouls you have, the better you are to win, if I'm reading it right. Okay? And so this model right here, it says that the output prediction, like our logistic regression model, is that we're going to be taking some intercept term plus a weight for our difference in how we're shooting and a weight for how different our personal fouls are. And what the logistic regression procedure that we talked about before, like the process of finding these betas does is, well, sorry, the process of fitting a logistic regression model is to compute these betas. Okay? All right? So we can threshold again. If we want to turn this into a classification as opposed to just predictions, we can threshold. So if I pick t equals 0.3, now the threshold is a plane that cuts through our two-dimensional surface here. And after we've finished applying this thresholding operation, we end up with basically the same analog before, where we cut this curve in two pieces. Everything that was below the line gets flattened down to blue, and everything that was above gets stuck up to the top orange. Okay? So that's what the two-dimensional visual picture looks like. Okay? So, oh, and on the right, by the way, the difference between these two is this gives me a probability. This model on the right gives me a class. So it just takes the probability and applies a threshold. In this case, 0.3. Yes? Good question. What will that thing look like? Is it a line? Is it something else? So this thresholded model, I want you to describe this decision boundary for me. Just think about it for a second. Like, what does it look like? Yeah. Say again? Oh, if we have 3 or more dimensions, what does it look like? We'll talk about that in a little bit. But here in this case, so your question actually is indeed, it is a line. And the way you can think about this, I didn't actually decide to do it in this. I thought it was too cumbersome to go open a notebook and show this to you. But if you just rotate this curve so you're looking at it overhead, so imagine going overhead and looking down at this thing, you would see this shape. So there is a line which separates the two predictions. This is the lose side, and this is the win side. So here, our decision boundary is a line. Before it was a point, now it's a line. And when I say before, I mean in 1D. There was an X, where if you were to the left of that X, you were lose. If you were greater, you were win. Now it is a line. Okay? All right, so that's a decision boundary. And it gives you a nice picture of what how your classifier thinks about the world. So you can think about it in a couple of different ways. One, you can think about it in terms of beta 0, beta 1, beta 2, and t. Or you can think about it just as this line. And any line you draw would be a different classifier. And you could have nonlinear boundaries, but for logistic regression, the model that we've talked about so far, you will only ever get linear boundaries. Later in the semester, we'll see a technique where you can get nonlinear boundaries. So why does this line exist? Well, it exists because this function here, right, if you look at the shape of this, no matter how you adjust the sharpness of this curve, it's still going to be the case that when you cut through it with a plane, you're always going to get a linear boundary, okay? Because this function's increasing in both of these dimensions monotonically. Okay. Yeah. All right. So we can overlay the data, and this picture on the right is what you'll very often see. So rather than just showing only the classifier, you'll often show the data on top of it. And this gives you a visual picture of how well your classifier actually did. So these are all the games from the 2018-2019 NBA season. And here we see that we can get just a visual picture of how well it does. And we can see that there's some games that would be quite hard to predict. In fact, with logistic regression, impossible to predict perfectly. So this game right here was an outlier. This is a game where a team was shooting pretty poorly, had about the same fouls as the other team, but yet they still won. And our predictor just has a hard time with that piece of data. All right. Okay. And another way of thinking about it is any blue dot on this orange side, as it says on the slide, you can think of these as the blue dots on the orange side. Yes, this is our model's predictions. So these are the false positives. Anything blue over here is something that our model would predict is a win, but was in fact a loss. This is something our model would predict was a loss, but in fact they won. Okay, any questions about decision boundaries? Okay, so it's just a really nice way of thinking about our classifier. It keeps things simple. Okay. All right, let's talk a little bit more about evaluating classifiers. Today's going to go short, actually. I'm a little surprised, but hey. So evaluating classifiers is a technique. We've been talking about different ways to say whether one classifier is better than another. And I'm going to repeat a little bit of that, but then we'll see some other ways of thinking about how good a classifier is. Okay. So as I noted, as we change our parameters, beta 0, beta 1, beta 2, and t, we're going to get different decision boundaries. And in a couple lectures ago, when Serge was teaching, we focused on 3 different metrics for evaluating classifiers. We talked about accuracy, which was the most obvious way to do evaluation of a classifier, but we also saw precision and recall, which are especially handy in the case of rare outcomes. We will now talk about 5 more different classification evaluation techniques, and there's actually many more than this. So I'm just going to review a little bit. Hey, it's a midterm practice since that's happening tomorrow. So this here is a picture, a nice little table reminding you what false positives, true negatives, false negatives, and true positives are. I think I said all 4 of them. And basically this says if the truth is that the class was 0 and our prediction was that it was 0, this is a true negative, and so forth. Okay? So as a reminder, your accuracy is just your true positive plus your true negative rate divided by n. How many did you get right? Your error rate was just 1 minus that. Your precision was true positives over true positives plus false positives. So it's of the predictions you made that this thing belongs to class 1, how many of them were right? And recall is true positives over true positives plus false negatives. So this is out of the actual positives out there, what fraction of them did your classifier find? So these top are the most obvious evaluation metric. The reason I call it singular is because they're just one's 1 minus the other. And then precision and recall are often used when you're thinking about rare outcomes. Say, we talked about spam ham, cancer diagnoses, that sort of thing. Now, I should note that some authors and our textbook, and I think possibly Surge, give the opposite ordering for these rows. So it goes 1, 0, 1, 0. But I'm doing it this way because, I don't know, I like it better, and it visualizes nicer for me. The code to make this table is easier. All right. So confusion matrices are one way that we can capture these 4 different categories. And you saw this on homework 7. And so I'm just mentioning it in lecture, so you also get to hear me say something about it. And so this confusion matrix just shows, if this is the unnormalized version of a confusion matrix, which just shows the raw counts. And it's very easy to write code. You had to do you messed around with some code in homework 7 to generate these tables. There's a much shorter one-liner that will actually generate a confusion matrix, no problem, where CM, if you have a 2-dimensional NumPy array, just this single line of code will spit out this nice picture. So here, I had to add some annotations. I kind of lied. I didn't show the X label and Y label. But other than the X label and the Y label, you can get this nice plot using Seaborn's heat map feature. Okay? And so here, this shows the number of true negatives and true positives. Okay, midterm review question. So, and also a chance for you to reflect on confusion matrices again. So I'd like you to do is I have 2 classifiers here, and I'd like you to think about or compute the accuracy, precision, and recall for each of the 2 classifiers shown, given their confusion matrices. So let me give you guys, I don't know, it's like a tiny midterm review time, so I'll give you 2.5 minutes. guys are less into doing this than I would expect. It's so midterm practicey. I'm still going to make you keep looking at it for... No, I'll cut it a little short. Okay, so on the left, our accuracy was 95%. So out of all the predictions, the ones where the true value and the predicted value match, that's 95, is the number that were correct, and then 5 of them were wrong. All right, precision. So this one's a little funny. I threw this at you as a strange question. So of my predicted ones, how many were actually 1? Well, we didn't predict any ones, so it's undefined. Recall of the actual ones over here. What proportion did we predict as 1? Well, none of them. There were 5 true, there were 5 actual ones. Uh-oh, that was my alarm. Shh. Okay. There are actually 5 ones. We predicted 0 of them. So our recall was 0. We missed all of them. So here, this is just a reminder that when it comes to situations like this, where we have relatively rare outcomes, this is also the spam ham example that Suraj gave, 95% accuracy doesn't mean anything if, well, all you do is you always just say no. Okay. All right, over here, this is maybe a little bit more typical example. So in this case, 0.8 is, so there's 100 total points. There are 2 where our prediction and our true value are the same. So 0, 0, and 1, 1. So there's 80 out of 100. Precision, well, there are, out of all of the predicted ones, that's these right here, how many were actually 1? 50 out of 70. And then recall, out of all of the actual 50s, out of all the actual ones, how many did we get? All of them. All right, any questions about this? Assuming perhaps not. Sorry, I don't know why I said assuming perhaps not, because if you had a question, you definitely wouldn't ask it then, because, I just told you didn't have one. All right. Okay. All right. So as we also saw briefly in Suraj's lecture, as we adjust our thresholds, we actually have our precision and our recall, they shift, right? So if we pick a relatively low threshold, that means that our predictions are going to largely be 1. And if they're mostly 1, well, that means that as we bring our threshold lower and lower and lower and lower, our recall is going to increase. In fact, if we pick a threshold of 0 or negative 0.1 or whatever, in that case, we'll catch all of the positives. All of the ones. We will catch all of the ones because our threshold is so low that we just say 1 for everything. So we expect our recall to go up and up and up as we decrease our threshold. But we also expect our precision to go down, because eventually we're going to say that everything is part of class 1, and so that's imprecise if we have any non-ones. Okay? So you can think about it this way. Very low threshold, we expect to get high recall but low precision, usually. And very high threshold, we have the opposite. And the corner is what we really want. We'd ideally like to have perfect recall and precision, but we may not be able to achieve that. Okay? Now, I should note real quick that I'm showing the precision on the y-axis and the recall on the x-axis. I like it better that way. I think it was done the other way before. So if this curve looks a little different than what you saw, it's because I switched it. Okay. Now, sometimes people talk about the area under this curve. I'm not going to do so today, but just mentioning that's the thing. All right, any questions about that? So it's one way to think about a classifier. You can look at just the accuracy. You can look at just the precision and recall for a given threshold. You can look at the precision recall for all thresholds. And really working with this, it takes a lot of practice. I mean, the very first research job I ever had involved what we'll talk about in a moment, ROC curves. And it took me probably a week or so of just working with them to really get them. Okay. All right. Okay. Even more evaluation metrics. So if you weren't happy, if you don't like just accuracy, precision, recall, like you want to be able to just spout off more and more jargon to your family when you go home for Christmas, if you're going home to some place, well, here's some more. So I got a couple more for you, false positive rate. And this one is, just another combination. This is the false positives divided by the false positives plus the true negatives. In this case, I'm giving a real-world example to give you a sense of what it means. So a false positive would be, what proportion of innocent people did I convict as a judge? So you want to ideally convict very few innocent people. You want to bring your false positive rate to 0. True positive rate which, by the way, is also the recall, is what proportion of guilty people did I convict? So why am I calling it true positive rate instead of recall right now? Because it's a different context, and I want to contrast it with the false positive rate. Okay? All right. Now you may say, doesn't this seem like too many? Yes, it does seem like quite a lot of assessments for classifiers, and in fact there's lots more, and I'll show you a little picture in a minute of more of them. Okay? All right, here's another fun one for you. Now I'm only doing this because if I just keep talking about a lot of concepts that are very, very closely related, your eyes will glaze over. So I'm requesting that you do this one more time. I know it's not that fun, but I think it's good so that you actually get what's going on. This time I'll only give you a minute. Just give me the FPR and TPR. So say 0 here is innocent, 1 is guilty. Give you 15 more seconds. Webcast people, I want you to do it for real. Okay, cool. Okay, so in this case, on the left, it's another kind of degenerate case. So in this case, the false positive rate is 0. So of the innocent people, okay, so if we look at this, the true situation here, so these are all the innocent people. How many did we convict? How many did we predict were guilty? 0. So 0 out of 95. On this side, what proportion of the guilty people did I convict? Well, there were 5 guilty people. And, did I mess up? Let's see. True positives. Here are the actual, we predicted 0. Did I mess this up? You guys did this problem, yeah. Should be 0 rather than 1, thank you. Okay, cool. Let's do it correctly. This is 0 out of 5. Let's show our work. Okay. 0 out of 5, and this is 95 out of, oops, sorry. This is 0 out of 95 equals 0, equals 0. It's a little ugly. Okay, come on. All right, cool. Okay, let's see if we got the other one right. See? So let me let you guys do the problems in case I mess up. On the other side, the false positive rate. Okay, so on this side, we are looking at the innocent people. Okay, so that's the true cases over here. And of them, we convicted, did I mess up again? 20 out of 50. Okay, cool. So do you guys agree with me this should be fixed? This is all to make sure you're paying attention. Okay, good? You happy that this should be 0.4? Okay, the other one, let's see if we got it right. Okay, so on this side of the guilty folks, what proportion do we convict? 50 out of 50. Okay, we got it good. So my accuracy was 50%. Anyway, I'm just going to try and get meta here and talk about my false positive rate on evaluation of false positive rates, but I don't know. It's a tortured metaphor. Okay, did I get the right answer now? Good. Okay, cool. All right. So what good are these? Well, the reason I brought these up, you can use them to evaluate your classifier as well, but our textbook discusses something known, we'll see as a ROC curve, and I had a bunch of experience with this long ago, and I'm just partial to them. Okay, so before we get to ROC curves, I want you to think about another question, which is just to motivate what I will be calling a ROC curve. I want you to think about the following question. If I set a threshold of 0, I hope you all agree that means we're saying everyone is guilty. If your probability is 0 higher, you're guilty, so you're guilty. And in the other case, if we set the decision rule or the cutoff or the threshold to 1, everyone is innocent. So I want you to think about the false positive rate and the true positive rate for each of these cases. I will only give you 30 seconds on this one. So here you don't even need to see the data or the model or anything. You just have to know what the thresholds are. These are the extreme cases. Okay, so I want to know the false positive rate and the true positive rate, at least for this case. if you set your threshold to 1, if you set your threshold to 1, then your false if you set your threshold to 0, that is, you say everyone's guilty, your false positive rate will be 1, because every innocent person is convicted, and your true positive rate is 1, because every guilty person is also convicted. Likewise, if you set your threshold to 1, then your false positive rate is 0, and your true positive rate is 0. Why did I make you think about that? Well, it lets you get a sense of, as you change your thresholds, how these two measurements will change over time. So for very low thresholds, we expect that these rates will be around 1, and for extremely high thresholds, they'll both be 0. So if we plot them together, we end up with a curve like this. This is known, by the way, as a ROC curve. I will not put the acronym on the slide, but it stands for Receiver Operator Characteristic. But I'll just call them ROC curves, because the name isn't actually that useful. Okay, so here, what I'd like you to do is think about yet another question. So this right here is similar to our precision recall curve. This is just something else called a ROC curve, where instead of plotting the precision and the recall, I'm plotting the true positive rate and the false positive rate, with the false positive rate on the x-axis, typically. We get a curve that looks something like this, and each of these points on the curve corresponds to a different threshold. So, using the question we just thought about a little, using the question we just solved together, try and figure out what these t's will be. Okay. So I'll give you guys a minute to think about that. And I know for some of you it's trivial, but for the others of you, I want you to just really think about it. Because if I just say it, it goes in your ear and just dies. There's a hint on the slide, too. But okay, so down here, is this a high threshold or a low threshold? Yeah. High, yes. So in the very corner will be the threshold of 1. In that case, that's just the problem we did before. If your threshold is 1, your false positive and true positive rates are both 0. As you decrease your threshold, as noted here, that was the hint I mentioned, we expect our true positive rate to go up and our false positive rate to go up as well. So this is good as we go up. Going in the y direction is good. Going in this direction is bad. Okay. All right. So this curve characterizes our regression model. Okay, so given a set of betas, this basically tells us how good those betas are. All right. Another way of thinking about it, here at the corner, we always classify 0. Here, we always classify 1. And as we as we decrease our threshold, we move along this curve. Okay, and we'll see a practical example of this a little later in lecture. Now, before I show you a practical example, let's just think about a couple of ideal cases. So one ideal case, or one basic case, is a model which just does a random prediction. So I say, hey, what do you think the chances are that the LA Lakers will win tomorrow's game? And you know nothing about basketball. So you know your choices are anything between 0 and 1. So that's how probabilities work, so you say 0.2. You don't use any information. I ask you, what's the probability the moon landing was faked? Manana. What's the probability the moon landing is faked? Guess randomly. 0.7. Okay, good. See, Manana has no idea. She doesn't know about the moon. She doesn't know anything about sound stages in Arizona or whatever. She just picked a random guess. Just a totally random number between 0 and 1. So if you did that, sorry, put you on the spot there. So a ROC curve for such a predictor would have a curve that looks something like this, right? So if you ran an empirical test, you would find that it would be a diagonal line. That's roughly what you would expect. It's going to do just chance, right? So you pick, if you pick a threshold of 1, it's obviously going to have a 0 true positive and 0 false positive rate. Around a half, well, you'd expect that it's going to be a half for both because it's just guessing randomly and so forth. Okay? So that's the kind of the worst case model you should ever build is a ROC curve that looks diagonal. That means your model is just randomly guessing. Okay? Here's the best model, the perfect predictor. So the perfect predictor says, hey, what's the chance the LA Lakers will win a game tomorrow? And it says 1, and it's always right. Okay, that would be an example of a perfect predictor, and it would have a ROC curve that looks like this. Now, it's a little funny to say that it's even a shape, but it's basically right. So if I pick a negative threshold, sorry, no, I don't really want to go into it. But basically here, it's always going to have a true positive rate of 1. And how have I confused myself? Let's see. Uh-oh, my brain's failing me. I know this is right, but I'm having a hard time explaining it. Say again? Yeah, false positive rate of 0 and a true positive rate of 1. Okay, yes, that's the way of thinking about it. Thank you, Manana. You saved me. All right. And so the better a model, the more it's going to resemble this perfect predictor, and the less it will resemble a random predictor. And so when we do a hands-on example in a moment, or not in a moment, in a little while at the end of lecture, we will see some ROC curves that lie between these two extremes. All right. So sometimes people try to summarize a ROC curve, right? So a ROC curve is itself a way to to evaluate a classifier. It gives you a shape. But you can also summarize the entire curve. Okay, we get a little meta here. So we can compute the area under a particular ROC curve. So for a perfect predictor, the area under this curve is 1. And for a random predictor, what is it? I'm not going to give you any time to think about it. Well, if we have this triangle here, what's its area going to be? Yeah. Half. Good. And so your predictor, when you build a classifier, or a regression model, I should say, it's going to have an area under its ROC curve of somewhere between 0.5 and 1. And what's nice about this area under curve measurement is it gives you a dimensionless quantity that characterizes the regression model. And what I mean by dimensionless is it doesn't have any units. So whereas mean squared error or average cross-entropy loss, it's like it's some number, but you don't necessarily know how to interpret it, at least if your data is on scale. Here, it's just a nice way of saying, okay, if I tell you I have a model whose area under ROC curve is 0.5, you know it's bad. And if it's 0.999, you know it's quite good. Is it possible to have a predictor with the area under the curve less than 0.5? So the ROC curve would be like down here or something? Yes. But that would mean your model is actually doing worse than randomly guessing. So it has been trained to fail, I guess, in some way. Okay? All right. Now, this is a little bit out there because we're not really in this class going to get a chance to dig into how one might use a ROC curve. There's no, at least right now, I guess project 3 or 2, when it's not in 2, it's not going to be in 3. So you're never actually going to do this. But I bring it up just because I happen to be partial to it. It's a fun way to evaluate classifiers. And if you're doing, say, the grad project and you're building a classifier, this might be a topic worth exploring. Okay? All right. So, classifiers. Why have I done all this to you? Well, I've done it partially because in the past iterations of the class, many of these other versions of the many of these other techniques for evaluating classifiers have been discussed. I just want to let you know that there's many choices. It's a little bit of a zoo. And if you go to this Wikipedia article here for confusion matrix, you can see that there's many, many different numerical assessments for classifiers. And so if you're reading papers out there someday, you may see people using things like false omission rate, or, I don't know, let's see, the threat score, and so forth. And in each of these contexts, you should just recognize that there are different ways of thinking about classifiers that people in different domains have found are useful for what they're working on. Now, so I show up here, we have these numerical assessments. We had 6 different numbers we could give back for a classifier. And then we had some visualizations. And then I make a note here that these 3, the area under the curve, the precision recall curves, and ROC curves, these all happen independently of threshold. That is, you only have an accuracy, a precision, or a recall if you've picked a threshold. The ROC curve is like a function of the threshold. You can see it, the curve involves different thresholds. So I should just know it's a little bit different. Like these are evaluated in the classifier after you've picked a threshold. These are before threshold. Okay. All right. Any questions about evaluating classifiers? How do you know which one of these many things to use? Well, probably if you're working on real-world problems, there's a set of common practices that people use to discuss to discuss accuracy in your area. So the research that I was doing long ago was on detecting mines using sonar data as a sophomore or junior or something. And in that case, we used ROC curves because we used ROC curves. There were many other things we could have potentially used, but that was just what we were all used to using and thinking about, and did a good job. Okay. There's actually, I'll add a link to this slide that talks about like an argument for why one might look at precision recall curves versus ROC curves. So I'll add it to the slide in case you want to read about it. Kind of interesting, but it's a little, specific. All right. I think it's break time. Then we'll talk about regularization. So I'm going to set a timer for 5 minutes. And let's do break. If you have any questions, I'll take them. Okay, mid-class announcement. So discussion tomorrow is dedicated to exam review. We also tried to keep deadlines from, not having things due, so there was no lab yesterday. Also, it was a holiday. And discussion tomorrow, 9 to 3, will be exam review, and the focus will be not on mini lectures where we re-explain things because the exam is happening a few hours after, and that would probably not be useful. But instead, we're going to focus on going through and solving old exam problems. Also, everything right? That's good? Yes, good. And then, as mentioned earlier, out loud, that is free attendance points. There's no yell key. Okay. So, where we were. So let's talk about regularization. And I would like you to think about this question. Okay, so we saw regularization for linear regression allowed us to keep our models from overfitting. To motivate today, I want you to think about this problem. So let's say, it's a good break problem in case you don't have anything to do, but all right. So I'm going to make you think about a question, which is, let's say we have a one-parameter logistic regression model. That is, its prediction is just beta x. That's what it produces. Or sorry, sigma beta x. Okay. So what beta will minimize the cross-entropy loss for this data? And I've given you 5 choices. And what I mean by the data here, to be very clear, I have an observation which has x equal to -1, and it's part of class 1. And I have an observation which has x equals 1, and it's in class 0. Okay. So I want to find the beta that minimizes the loss. So I'll give you guys a minute to think about that on top of your break minute. Spoil this. So it turns out the best beta here is -infinity. Why is it -infinity? Well, if we think about what our logistic regression model is, it's sigma x transpose beta. In this case, x is just a number, right? It's just a scalar, and beta is just a number. And sigma, reminder, is 1 over 1 plus e to the minus t. So in this case, our predictions are, sigma of, this is, of course, ever so slightly not rigorous mathematically, but it's close. We can talk about limits, I guess, instead, but that just needlessly complicates things. And so here, our prediction is that it's going to be sigma -infinity of x. So for a very large x, our prediction, let's see, so if we pick, if I have a negative, let's see, if my x is -1, this is e to the -infinity, which goes to 0. So 1 over 1 is 1. If I pick an x which is positive, say 1, this will be e to the infinity, which is infinity. 1 over infinity is 0. Okay. So that's the best beta, is -infinity. It has this very sharp curve here, right? If we picked, say, -2 or something, it just wouldn't be quite as good. It'd be close. But -infinity, the cross-entropy loss that it yields is 0. That's pretty good. You can't do better than 0 loss. Okay. All right. Now, I don't like beta equals -infinity. Not a great answer, because it's just bizarre to have a huge crazy beta like that. Another way of thinking about this, other than just looking at the raw prediction curve here, is to think about the cross entropy loss. So I'm just showing you, you can't compute this in your head, but this is the curve showing the mean cross entropy loss as a function of the beta we pick. So if you do gradient descent on this, where's it going to go? We go down, 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 down to -infinity. Okay? So that's the best answer. The smaller the beta you pick, the better your cross-entropy loss. Okay? So what's one reason why this is a good model? Like, in what sense is it a good model to say that beta equals -infinity is our model? Yeah. Yeah. Great. Predicts perfectly every time. No loss. What's the reason why it's a bad model? Yeah. So negative infinity isn't really defined. It seems weird to use in a numerical setting. Sure. Yeah, that's a good answer. I need another one. Something kind of more like something in terms of loss. So this is just one data set. This is our training set. What would happen if we used a test set and we got something wrong for this model? So imagine if I go back to this picture. Let's say I get an x over here or something, and we get it wrong. What will be the loss for that data? Like if I make a wrong prediction over here, what will be the cross entropy loss? Anybody know? Yeah. It'll actually be infinite, so it's not zero, it's the opposite end. So if you make any wrong predictions, if your predictions are all exactly 1 or exactly 0, and you get any of them wrong, the cross-entropy loss will be infinite. Okay, so I'd say this model is overconfident. Just that's the way I think about it emotionally, right? A single misprediction on a test set is going to give me an infinite loss because they're going to have a log of 0. So it's good in the sense it minimizes our training loss, but it's bad because it's overconfident. Okay. Let's go back to the beginning of lecture when we talked about decision boundaries. Okay. So data that can be separated with a line is called linearly separable. Okay, so this here is an example of that. This is technically kind of, I don't want to go there. It's separable by a line. Hope you all agree. And it turns out that logistic regression, if you run it on linearly separable data, that is, what do I mean by that? I mean that the data can actually be separated by a line. So here, all of the orange points are to the left of some line, and all the blue points are to the right of some line. They will always yield betas. If you run it on a computer with infinite precision, it will give you infinite betas, okay, or infinite magnitude betas. So on a real computer, of course, if you run gradient descent, you're going to eventually just get stuck. And maybe you'll get stuck at, I don't know, beta equals negative 30 or something. But that's still quite large in terms of magnitudes. Okay. So if you ever have the bottom line here, if you have data which is linearly separable, then when you use logistic regression with no regularization term, you're going to get really big betas. Okay. Here's another example. So I find it actually kind of hard to think about in one-dimensional case personally, maybe because I'm so used to looking at plots like these. But this is showing you for the data set, the iris data set, which you may have seen. I don't remember. Have we done that actually this semester in this class? You guys know about these guys? No. Okay, well, they're different flowers. There's one called a setosa, one called a versicolor. I swear there was something somewhere. But anyway, this is the size of the petals of the flowers. And we want to try and predict which species it belongs to. So this is the decision boundary for a model that I trained. And we can see that they are actually separable. All of the plants that are called setosas. Okay, let's see. What are they called? Setosa. Let's see one. Okay. Hello, setosa. There you are. Versicolor. Okay. All right. Oh, that's that's not good. The plant. Not the skin thing. Okay. I should have done that. Okay. Wait. Okay. Cool. So they look pretty similar, but I guess their petals are different. Okay. All right. So those two different plants, you want to try and tell them apart based on measuring them. And it turns out that in this classic data set from way back in the day, in the 20s or so, I think I maybe even talked about it in lecture, I'm not sure. They are linearly separable. Given these two measurements, you can separate them with a line. There are other lines that separate them, by the way. You could do a vertical line or horizontal line. Here I'm doing a diagonal. So if I run logistic regression or fit a logistic regression model to this data, the loss surface that I'm optimizing looks like this. Now I'm going to note this is not the probability on this vertical axis. This is the mean cross entropy loss. And I'm not using the same color scheme. See, look at these loss colors. This is not blue and orange. This is some other color scheme. As I pick larger and larger beta, my cross entropy loss goes lower and lower and lower. Now it's very small over here, but it'll get lower and lower and lower the bigger betas you pick. So I tried running this on my computer just to see what would happen, and it settled at beta 0 equals negative 40.5, beta 1 is 10.77, and beta 2 is 17.61. This is an intercept term. These are for my two parameters, or my features. Okay. Now this right here I call them large betas. Oh, actually, just to address this so that it's out loud in case you're wondering, this note at the bottom, this loss surface, there's actually 3 parameters, beta 0, beta 1, and beta 2. But I'm only showing 2 dimensions because that's all I can plot. Technically, there's some variation with beta 0. So I just picked an arbitrary beta 0 for this picture. Anyway, so if you run logistic regression on it, this is a very long-winded way of saying, you know that minus infinity that you guys came up with on your own? That happens here too. We end up with really big betas. The optimal beta are actually infinite beta 1 and beta 2, but whenever we run these, well, actually, sorry. I should say the optimal beta are really, really, really big numbers that have the appropriate ratio between beta 1 and beta 2. When I ran it on my computer, I ended up with these. Now, you might say, these betas don't seem very big. It's only like 10 or 15 or 20 or something. But what do we do with betas in logistic regression? We multiply them by x's, and then we exponentiate them. So having numbers that are like 20 and exponentiating something to the 20th power is pretty big. Okay. So to drive that home, just to give you a sense of what I mean, let's say I want to know the probability that we have a versicolor, given that the length is 1 and the width is 1. Well, we would just plug in we just do the sum of these 3 numbers. You can think about that later. And so the probability in this position is 5 times 10 to the minus 6th. That's pretty small. And it's perhaps not reasonable, right? Because there's probably a few freakish versicolors out there that are small because maybe they didn't get enough food or water or something. And to say that the chance is only 5 times 10 to the minus 6th seems a little perhaps extreme. Okay. Bottom line, if your data is linearly separable, you will get big betas. Big betas is like 2-digit betas. Okay? So how do we avoid overfitting? How do we avoid really big betas? We use regularization. Now the nice thing is that the generic technique that we described called regularization works here exactly the same for logistic regression as it did for linear regression. So if standard logistic regression looks like this, I want to find the beta that minimizes my average or my empirical risk here, where I pick some loss function, say cross-entropy loss. Now I'm just adding a regularization term. It's exactly the same as before. Okay. So, if you have linearly separable data, you should use regularization. Otherwise, you'll get giant betas. Okay. So here is an example. If I pick a lambda of 0.2, then I get betas that are more reasonable. This picked an intercept of 0, a beta 1 of 1.07, and a beta 2 of 1.05. I can't remember if I had centered the data or not, but anyway, I get smaller betas. That's the bottom line. Okay. So as with linear regression, when you use regularization, just a reminder to make sure that your data, that you've put everything into standard units, that you've scaled everything so that we don't have widely different ranges for our different parameters or for our different features. Because if you have widely different values, that is like value ranges for your features, then, well, your betas are going to get unfairly penalized. We've already said that in the past, so I don't know if I should talk about it again. All right. Okay. Let's see a little demo of this whole thing happening.